Today we're going to look at Chapter 12, Reactive Systems, and here we're looking at the combustion of hydrocarbon fuels. And so with hydrocarbon fuels, that's much of what is burned in automobiles and furnaces. It's a lot of the energy source that powers society. And so if we look at liquid or gas hydrocarbons, we're looking at something like CXHY. And so we don't know what they are, and very often it'll be a mixture of many individual ones. For instance, octane is C8H18, dodecane is C12H26. And he's following in whatever the end model is you learned in chemistry. And so these are the ideal ones, so we tend to use this for gasoline and this for diesel fuel. And so these are the ideal models for that. And for alcohol, you replace an H with OH. So we'd have CXHY OH. And so if we wanted to look at alcohol fuels, we do that. And now what we want to do is look at the combustion process and how we do that, and it's fairly straightforward. We have reactants and we have products. So if I were to oxidize carbon, if I were to burn carbon, I would get carbon dioxide. So I'd have C plus O2 yields CO2. So I have 1 mole of C plus 1 mole of O2 yields 1 mole CO2. So this is not, we don't have conservation of moles, but we do have conservation of mass. So we have 12 kilograms. I look at the molecular weight of this, plus 32 kilograms yields 44 kilograms. So the combustion equation that we write is a conservation of mass equation. And now let's do this for hydrocarbon fuel. We'll pick a simple one, CH4 methane. So we'll have CH4 plus O2 yields CO2 plus H2O. So we're looking at complete combustion of the hydrocarbon fuel, and so the oxidation of carbon goes to carbon dioxide completely, and of hydrogen goes to water. And what we do is we balance the carbons. So when we go through doing this, we'll do this for more complex hydrocarbons, but let's see first. So we have a C balance. So I have 1 on the left, yields 1 on the right. So I have 1 there. And now we do a hydrogen balance. So I have 4 here. So I need 4 there, so I have to put a 2 here. So I'm balancing that. And now we do an O2 balance. And we're going to go the opposite way. So I have 1 O2 plus 1 O2. So we're balancing for O2, not for oxygen. So I now need 2 O2s. And so I need a 2 here. And there we balance this equation. Now, mostly we don't oxidize things with oxygen only, we use air. And let's look at the Molal analysis of air. we're going to say it's 79% nitrogen, 21% oxygen. Oops, I have to put in nitrogen. Now there are various other gases around, but we're going to assume that. So if we look at this, 79 divided by 21, we'll see there are 3.76 moles of N2 per mole of O2. So for each mole of oxygen, we're going to have 3.76 moles of nitrogen. So now let's balance this reaction equation with air. And so we'll do this for just the minimum amount of air that's needed, and that's called 100% theoretical air. But first, let's write the equation. So I have CH4 plus, and I'm going to leave a little space here. I have O2 plus 3.76 N2. So that's the air. That's the air. And this is going to yield CO2 plus H2O plus H2O plus, I know I'm going to have some N2 left over because it doesn't enter into the combustion. I do the same thing that we did before. So I do a carbon balance. One yields one. I do a hydrogen balance. 4 yields 4. So I need a 2 in front of here. And now we're going to do the O2 balance. And I have one O2 plus one more O2, so I have 2, and I need 2 here. So the 2 goes out in front. So then all the oxygen is used. And so what's left over is the nitrogen, so I have 7.52 nitrogen that gets carried along. And so this is balanced for 100% theoretical air. This is the minimum that you need for complete combustion. And by complete combustion, we mean that the fuel, there's no fuel left over, we don't have any carbon monoxide, everything is perfectly oxidized. Now, very often what we need to do is have more air than is minimally required. And so this is called excess air. So we need more O2, really. It isn't the air we need, it's the oxygen. More O2 than minimum. So this is called excess. Called excess air because that's where we get it from. Now, why is that? Why do we need more? So if I'll take a little drop of oil as an example so we see what that is. So I have a little bitty droplet of oil. And what happens when it burns is I start getting the products of combustion around it. So here's the fuel, and then I start getting my products going around it. And so here's the O2 out there, and the O2 wants to be part of this reaction, but it's blocked by the products of combustion. So a lot of times we will look at ways to mix this up and all that stuff, but part of why we need the excess air is to make sure that the oxygen that's in the air can come in contact with the fuel. So anyway, back to excess air. Let's say we need 25% excess air. Or 125% theoretical. So what we do is we take that equation and we just multiply the air by 1.25. So we balance it for 100%, and then we compensate for what's left over. So let's rewrite that, and I have CH4 plus 2 times O2 plus 3.76 N2 yields CO2 plus 2H2O and now, because there's excess air, there's going to be more air left over because this is for 100%, I want 125, so I multiply by 1.25. So when I do that, there's going to be oxygen left over and there's more nitrogen. So in this case, we have plus 0.5 O2 plus 9.4 N2. And so now we've balanced the equation for 125% theoretical air. Very often we use air-fuel ratios and fuel-air ratios. So we could have RAF is equal to the moles of air over the mole of fuel. Notice that the reaction equations that we do are always balanced for 1 mole of fuel. So everything we do here is balanced for 1 mole of fuel. And then everything else is based on that 1 mole of fuel. So now the moles of air, so if I look at this and 1.25 times 2 times 4.76 divided by 1. So the moles of air is 1 mole of this plus 3.76, so there are 4.76 moles of air, and that's where that comes from. So this is 11.9 moles of air per mole of fuel.